Now we'll be factoring trinomial squares and difference of squares. Trinomial squares has three terms, and it's not factored any differently than we were doing before. Two sets of parentheses, break up your x, both positive. Two numbers that multiply to 16 that add to 8. They just happen to be the same factor, so you can write it in exponential form or an expanded form. Two numbers that multiply to 36 that add to negative 12, negative 6, negative 6. So two sets of parentheses, same sign, both negative. Two numbers that multiply to 9 that add to 6. I can write it in expanded or exponential form. It doesn't matter. It just has the same factor. Here, I do not have a leading coefficient of 1. I want to first check if I can divide everything by 2, and I can. So I'm going to divide each term by 2 first. Pull that GCF out first. Then set up my two sets of parentheses. Same sign, both negative. Two numbers that multiply to 25 that add to 10 is going to be 5 and 5. So these perfect squares are what makes it a trinomial square. However, you're not factoring any differently. Positive, positive. Two numbers that multiply to 81 that add to 18, 9, and 9. Here, I'm going to put this in the correct order first, leading coefficient first. My x term, my constant, making sure the signs are the same because the a is positive and that's good. Two sets of parentheses, break up, same sign, both negative. Two numbers that multiply to 36 that add to 12. It's the same one as up here, 6 and 6. Alright, next, difference of squares. The difference with this one is now I only have two terms, and it's a specific formula. And it has to be two terms, and they have to be perfect squares, and it has to be subtraction. Difference of squares. Perfect square, perfect square. When I do have two terms, like this, I square root the first term, square root the second one, and it's one of each sign. That's the formula. So, two terms. Perfect square, and it's a difference, subtraction. Two sets of parentheses, I break up my x, square root it, the square root of 4 is 2, 2 and 2, and it's one of each sign. If I were to FOIL this out, plus 2x, minus 2x, minus 4. This works because these middle two terms are the same with opposite signs and they cancel. That's why this has to be subtraction, because these have to be opposite signs and C is always negative for this to work. So, two terms. Do you have a perfect square? Yes. The square root is 2x. Minus, do you have a perfect square? Yes. So you go ahead and factor. Square root the 4x, 2x, 2x. Square root the 9, 3, 3. One of each sign. So two terms. Perfect square minus a perfect square. Two sets of parentheses, square root the y, square root my 36. One opposite signs, the order doesn't matter. Any even exponent is the perfect square. So you have two terms, they're both perfect squares, and it is subtraction. So 4x squared is the square root of 16x to the 4th. One of each sign. Square root of 49 is 7. Now, I still have exponents, so I want to check to see if I can further factor, but this is positive, I cannot factor, and that is not a perfect square, so I am factored as much as I can. So do some more examples. Okay, I have two terms. I have a perfect square minus, that is not a perfect square. I do not have anything in common, and I do not have a difference of squares. It is not factorable. Here, I don't have anything in common, but I do have a perfect square minus a perfect square, so it is factorable. When I factor this, I want to leave the terms in the order that they are. So the square root of 49 is 7, one of each sign. The square root of 25t squared is 5t. Here, two terms, perfect square minus perfect square. I'm going to square root this term first, one of each sign, x and x. Perfect square minus perfect square. Square root 9w, one of each sign, square root the 1, 1 times 1 is 1. Alright, here 81x to the 4th is a perfect square, minus 1 is a perfect square. So 9 times 9 is 81, and then x squared, half of the 4. One of each sign, square root of 1 is 1. If I still have exponents, I want to double check, am I factored completely? There is no formula for a positive with two terms, a sum of perfect squares. But I still have a difference of perfect squares over here. So always watch out if you have a power of 4 and a 1. See if you can't factor that again. So I'm going to keep factoring this. Square root of this is 3x, one of each sign, and the 1 times 1, and now it's factored completely. Anytime I see a 4, I'm going to make sure that I double check to see if I can keep factoring. P squared, 4 and 4, one of each sign. The positive will not be able to be factored anymore, but the subtraction or the difference is still a perfect square minus a perfect square. So I can keep factoring. And now it's factored completely. Here, plus, I cannot factor this. Cannot factor a sum of perfect squares. Here, I see they're both divisible by 5. I need to pull that out first. GCF my two terms. 5 times 1 would get me 5. 5 times 4x squared will get me 20x squared. Then I want to look, do I still have a difference of perfect squares? And I do. 1, 1, plus, minus, 2x, 2x. And I'm factored completely.